Welcome back to Chapter 1.2, Expectations, Variance, and Covariance as Geometry, Part 9 of 10. In Part 8, we saw correlation is a cosine, and risk adds like vectors. Two assets needed only 3 numbers, but a real portfolio holds dozens, and Maya's lender tracks thousands of loans. Writing a separate cross term for every pair becomes hopeless, so we collect them into one matrix, the covariance matrix sigma, which is not just storage, it is the very object. Week 2's matrix regression multiplies. In this part, we build it and read off its 2 structural facts. Here is the result in one sentence. For a vector of random returns, the covariance matrix sigma stacks every variance on the diagonal and every covariance off it, so that the variance of any portfolio is the single tidy expression W transpose sigma W. Define sigma entry by entry. The JK entry is the covariance of return J and return K. The diagonal entries are a return's covariance with itself, which is just its variance, so variances live on the diagonal. For Maya's 2 assets, sigma is a 2x2 matrix with 0.04 and 0.01 on the diagonal and sigma 1, 2 in both off-diagonal slots. Compactly, sigma is the expected outer product of the centered return vector with itself. A portfolio with weights W summing to 1 has returned W transpose R, and its variance unpacks as W transpose sigma W. Check it on Maya's case and you recover, term for term, the weighted variance formula from before. 2 structural facts come along automatically and both matter later. First, sigma is symmetric. The JK entry equals the KJ entry, because covariance is symmetric. Second, it is positive semi-definite for any weight vector W. The quadratic form W transpose sigma W equals a variance and therefore can never be negative. That is just a statement that no portfolio can have negative variance, geometry forbidding the impossible. Now, the failure mode to flag. If 2 assets are perfectly correlated, or one is a linear combination of others, say a fund that is exactly 60% of asset 1 plus 40% of asset 2, then the columns of sigma become linearly dependent. The matrix is singular and it has no inverse. That sounds abstract until week 2, where the ordinary least squares estimator inverts X transpose X, a close cousin of a covariance matrix. When regressors are perfectly collinear, that inverse does not exist, and the regression cannot separate their effects, the same singular matrix wall met from the other side. To summarize Part 9, the covariance matrix sigma stacks variances on its diagonal and covariances off it, so any portfolio's variance is the single quadratic form W transpose sigma W1 line that works for 2 assets or 2,000. 2 structural facts come free. Sigma is symmetric, because covariance is, and positive semi-definite, because its quadratic form is always a variance, and no portfolio can have negative variance. The failure mode is singularity. When assets are perfectly correlated or collinear, the columns become dependent, the matrix has no inverse, and week 2's regression hits exactly that wall. In Part 10, our finale, we rescale sigma into the correlation matrix you actually plot, the heat map of cosines, and wrap up the whole chapter.